Well, it's 6 p.m. now, so we could
all right,
start.
so let's get started. I'm happy that Simo Huotari. Everyone should mute their mics so there's no echo, please. That Simo Huotari from University of Helsinki is going to give us a talk today. For others who want to give talks, please email me, seidler@uw.edu, or take a look at the shared folder that's up on the screen right now, and let us know what we can do. You'll see that yesterday's lecture is available there as a pretty big MP4 file. I'm on the learning curve to figure out how to put that kind of thing on YouTube so it can be streamed more conveniently. And I'll send out information about that once an appropriate teenager teaches me how to do it. The other thing is, as you have questions during Simo's talk, type them into the chat. And at a few times during the talk, he'll pause for questions, and I'll try to paraphrase the questions or refer to a particular questioner to unmute their mic and have a discussion with Simo. So without further ado, let's hear from Professor Huotari.
Thank you very much, Jerry. And first of all, I mean, thanks, Jerry, for this great idea of having this global journal club. I think this is something very important and needed at this point of time. And I hope that all of you are in okay and in healthy state, and your families as well. So, yeah, let's go forward. I'm also learning how to use this thing now. So I try to move on to the next slide. Well, all right. So, yeah, the idea of the journal club was to choose a couple of articles to talk about, and I chose these two. And well, Jerry started yesterday to talk about X-ray Raman spectroscopy, and I thought that it would be useful for me to actually follow on that. So this series of lectures are by no means meant to focus on X-ray Raman. By accident, this happened to be now the two first lectures focusing on that. So I would maybe briefly introduce again the X-ray Raman scattering spectroscopy that Jerry already did, but I have some of my own views probably on that as well. Then I will focus on something that we developed for X-ray imaging using the X-ray Raman spectroscopy or inelastic scattering, and then some examples of complex systems that we have studied, and where the imaging actually comes very handy. So let's start with the X-ray Raman. Very short introduction, because Jerry did that already yesterday. So what we do here is an alternative to soft X-ray absorption spectroscopy. In XAS process, a photon interacts with the system getting absorbed, and as a result, an electron is promoted from an inner core shell to the unoccupied states in the one electron picture, right? So what we do in inelastic scattering is that we come in with a photon that has much higher energy than the binding energy or the excitation energy for the electronic system. Nevertheless, it's possible still to create the same kind of excitation, and due to energy conservation, another photon must be created and emerging from the system with a smaller energy now than the incoming photon energy is. So typical IXS inelastic scattering beamline could use 10 kilo-electron-volt photons to study processes that are in the electron-volt and 100 electron-volt, maybe kilo-electron-volt range. So one detects the outgoing photon with a diminished energy, and then deduces the spectrum of these excitations. From the electron system point of view, the excitation is exactly the same in both XAS on the left and in the X-ray Raman on the right. The name Raman comes as an analog from the optical Raman spectroscopy that produces vibrational milli-electron-volt range excitations, but X-ray Raman is then equivalent to soft X-ray absorption, creating core electron excitations. And this was dealt very nicely yesterday by Jerry. But actually the spectra look a bit more complex than that. So the spectra are encoded in this S of Q omega, which is the dynamic structure factor. And this is a simulation for how the spectra would look like for diamond. We chose a particularly simple system, just carbon atoms. And the spectra now are encoded here with red being high intensity, and the height of this pillar being the intensity as well. And they depend on two variables. Because this is a scattering process, we have a momentum transfer Q, and then the energy transfer omega, because it's an inelastic scattering process. So they are represented here on this axis. We have the energy transfer in electron volts, and here momentum transfer, not in arbitrary units. AU here means atomic units, so it's in terms of the inverse Bohr radius. The smallest momentum transfers are here in the back. And you can see this kind of broad feature, which is at the low momentum transfers, one probes basically large-scale excitations, large-scale phenomena on the length scales. So these are typically collective valence electron excitations when we have a condensed matter system. And then this disperses smoothly into Compton line shape at higher momentum transfers, where then one probes more single particle excitations. But here in the middle, we have the sharp discrete step, which is now the X-ray Raman line, which is basically due to the core electron excitation. So the carbon 1s core electron has a binding energy of about 300 electron volts. So you see the sharp onset at 300 eV or around. So it looks like a minute little detail here, but actually if you zoom in and you can see all the chemical information that is buried there, it's similar to XAS spectra. So these are real X-ray Raman spectra from different aromatic hydrocarbons in condensed states. So you can see that all these molecules have different spectral fingerprints, and one can use this for chemical analysis, for example. This would be exactly the same as the XAS spectra, but now done by hard X-ray method. So what is the use for this hard X-ray method? Because the information would be basically similar, is that one gains an access to extreme conditions and different kind of in situ environments. For example, diamond anvil cell, which is otherwise impermeable by soft X-rays. One has a bulk sensitivity. Sometimes you want to study what happens on the surface. Sometimes you want to go below the surface. So this is a bulk sensitive method, of course. Something that often is forgotten is that in XAS, those who are intimately working with that know that there's sometimes problems with spectral saturation, because the self-absorption can become so large that this has severe effects on the spectral shape. And actually, X-ray Raman is always free from this effect, which is also something very useful. And it's not limited to dipolar transitions, and you can go back to yesterday's talk by Jerry of the different transition matrix elements. So diamond anvil cells, different kind of in situ environments. You don't have to worry about that. Your X-rays go through most of the complicated systems, so you can do in situ electrochemistry, catalysis, hydrogen storage, many other things. So because it's useful, I think I would like to show here a typical beamline setup. So this is a view from side, and this is a view from top of a typical beamline. You prepare your incident beam, focus and monochromatize it, and hit it on the sample. And then you have a crystal analyzer spectrometer, which is often in X-ray Raman based on the so-called Johan geometry. Basically, on a Rowland circle, you have a spherically bent crystal analyzer that then focuses the radiation onto a detector, selects the wavelength through Bragg's law. This is an image of a typical analyzer crystal. It's a silicon or germanium single crystal wafer typically, and spherical curvature. This is an old instrument. This is actually from the NSLS-1 in Brookhaven, X25 beamline. And the idea is that the beam comes in from here. It hits the sample, it gets scattered by the sample, and it's collected by this analyzer crystal here, focused onto the detector. So that was basically a very simple setup. If you didn't really like the outlooks of it, here you see actually the Rowland circle. And if you didn't really like the looks of it, you could hide it behind a helium bag just to get rid of air absorption. But of course, the times have passed, and the development of the instruments has gone forward. So here I show as an example an instrument available at the ESRF, ID20. It's a modular design of 72 of those spherically bent crystal analyzers on 6 different modules, 3 of them in vertical and 3 of them horizontal, and the scattering angle can be varied. So it made it a cover of the Journal of Synchrotron Radiation, which made us, of course, proud. This is called colloquially the Stargate of ESRF because it has an obvious resemblance to the Stargate, right? So this is actually how it looks without this heads of these modules of the vacuum chambers. So they are arranged in a fashion that we have 12 spherically bent crystal analyzers in a 3x4 configuration. And this is Roberto Verbeni after he collected all the analyzers and installed them. So, right. This is some instrumentation and basic of the scattering. Are there any questions at this point?
Thanks, Simo. Yeah, we have a question. When you do XAS on diamond anvil cells, you often get glitches from diffraction from the accidentally hitting the Bragg condition on a diamond in the DAC. Mm-hmm. Is there a similar problem with X-ray Raman?
Yes and no. I mean, I will actually show how we can get rid of the signal coming from the environment. And the other thing is that we often do the experiments through a gasket, which is for X-ray penetration purposes made out of beryllium, and this is a polycrystalline system. So these glitches can be nuisance if the sample is a single crystal, but I will show how to actually get rid of that in the next part.
All right, great, thank you.
All right. So imaging, why and how we could do imaging with this. So this is the Johan geometry. We have a spherically bent crystal analyzer arranged in a Rowland circle where the sample, detector, and the crystal are all aligned. And then we just started to think about that if the sample has some heterogeneous nature, it of course will get also imaged onto a detector if we have a position sensitive detector, because basically this crystal at the same time acts as a mirror and not, it's a focusing monochrometer, right? So this turned out to be real. So this shows a cartoon of the idea. An incident X-ray beam comes in here through a sample that has several different kinds of structures. This spherically bent crystal analyzer is now the heart of the system. It selects the wavelength with an electron volt or sub-electron volt accuracy, and then it focuses the radiation that it selects onto a detector. And if you put here a pixelated area detector, it can then discriminate the signal that comes from the green part, focuses it in here, then from the red part, which gets focused here. So this is very easy way to do scattering-based imaging. It's dark field imaging in a way. So if your beam is a pencil beam focused in both directions, then this one dimension that it's penetrating through the sample will get imaged onto the detector. Basically, this imaging comes for free because if you would place here a zero-dimensional point detector, you would just integrate over all these regions, and this doesn't come with the cost of intensity, for example. So it works quite nicely in these complex environments when we can now get rid of the contribution to scattering from the different parts, other parts of the setup than the sample that we want. So you can get these kind of images. This is actual image from the detector. This is a diamond anvil cell. So we have a little sample here pressed between 2 diamonds. And then this beam goes through, in this case, through the gasket, which is made out of beryllium. And well, one can see this beryllium gasket shape here, the diamond cullets here, and then the sample is here. You cannot really see it directly, but you can see that it absorbs because after the beam is coming from here, right? And then it absorbs a little bit, and then after the sample, there's less scattering from this beryllium gasket afterwards. So now I can simply focus on this interesting region, the pixels that could generate this region of interest where the sample is, and then only look at that. One can get effectively rid of all the background scattering from the cell without any kind of slits or solid slits systems or collimators, which is pretty useful. And these are I don't know if you can see it very clearly. These are typical images of this pencil beam going through the system. So there's a little increased intensity here, which is the sample, and then we can simply not focus at all on the analysis of this part that comes from the other parts of the cell than the sample. So that gets rid of spurious reflections and other stuff from the other parts. That was a very brief introduction of how we do the imaging, and then I would show some examples of the samples. So questions at this point?
Yeah, Simo, thanks. That's great. What kind of spatial resolution can you get with this method, and what do you think is the limiting factor?
At the moment, the limiting factor is basically the detector pixel size, because we need a photon counting detector. These are typically in the range of, for example, the Medipix family has a 55 micrometer pixel size. So with a 1-to-1 focusing geometry, the limit is basically that. And then if the pixel size of the detectors could be improved, then the limiting part will be the crystal optics, how perfect this spherically bent crystal analysis can be made. We are not there yet, because basically the detector is at the moment the limiting factor.
What about the intrinsic rocking curve? Doesn't that come in?
At a certain point, it would. Yes.
Yeah, but that's going to be around 100 microradians or something like that. So I'm surprised that you're not already limited by that. But maybe
no, because the spectrometer operates at near backscattering conditions, so the Bragg angle is close to 90 degrees. So for the spatial resolution, this doesn't come into play at this point.
Okay. All right. Thank you.
All right. So some examples. I actually couldn't resist showing this one. Disclaimer is that I'm not a part of this study, so I'm not an author on this paper, but I picked it up from Science Advances 2019. And well, if you have X-ray Raman spectroscopy, which can measure, for example, the carbon spectra, X-ray spectra from a bulk specimen in a position-sensitive way, of course, there are many kinds of samples that would be interested to study if you have a buried system. This is actually a 53 million year old fossil shown here. This is an ant buried in amber. And now the people were interested to find out whether some of this soft tissue of the ant has remained. And now, of course, it's buried in amber, which is carbon-rich material, and it's a carbon-rich system that you want to study, and you don't want to break it up. So X-ray Raman was used to investigate what is inside here. It turns out that you can see some renderings of the 3D images of the ant, and every voxel now carries an X-ray Raman spectrum, so I can look at the chemical fingerprint, what is inside. And it turns out actually in this case only the chitin shell remained, while the soft tissue had been replaced by the amber over time. So but that's an interesting example of what kind of things one can do with this imaging technique. And one thing where it's used quite often is, again, this complex sample environments, diamond anvil cell. This is a typical diamond anvil cell used for this kind of studies, panoramic one, which means that it has as large opening angle for scattered radiation to go out the sample as possible. And for water studies, typically the system size, the sample size inside the diamonds is in about some hundreds of microns, like 400 micrometer is a typical one. One needs quite large diamonds in this kind of study. At the ID20 at the SRF, the X-ray beam size is 10 by 20 micrometers, and probably 10 by 10 now with the upgrade project. So one can really look in detail of what's going on in the systems in high pressure. And this is how it looks on the beamline. The pore sample is being investigated by all these 72 spectrometer analyzer crystals. The incident beam comes in from here, focused by K-beam mirrors. Diamond anvil cell is here, and the scattered radiation is then analyzed by these modules. What one expects to see from water in this case, It's basically a very good system for X-ray Raman in high pressure because the oxygen KH is the highest energy X-ray line that you have there. And it's 500 electron volts, and this is of course in the soft X-ray range. Typically this is for the molecular orbitals for water, single water molecule. We have basically the 1s oxygen orbital here, and then you have the HOMO-LUMO gap, and then basically one sees in the spectrum these unoccupied orbitals. So one gets this indirect structural information through the density of empty states when one looks here. And at the dipole limit, the X-ray absorption spectrum is limited to dipolar S to P transitions, but X-ray Raman spectroscopy gives also an access to other excitation channels. So it's in principle a tool also to look at other molecular orbitals that would be otherwise forbidden from a regular X-ray absorption spectroscopy. So what one expects to see that we come in with a photon that excites the inner core shell electron and puts it into the unoccupied orbitals. So the first one here is in a gas phase of a strong pre-peak that will actually be seen also in condensed phase water systems. So then we measure the intensity of the outgoing photons and their energy spectrum. So actually, this is what you would normally see from an oxygen KH in water. This is actually temperature dependence of those spectra. So you see typically three regions: a pre-edge that stems mostly from these LUMO orbitals in the gas phase, and then we have a main edge and then a post edge. Then these three distinct regions go so that the pre-edge seems to be, for example, if you increase temperature, it gets increased in intensity, and it's often taken as a fingerprint of breaking hydrogen bonds, because when you increase the temperature of this system, you expect that these hydrogen bonds are broken, and this is very strong actually in the gas phase, where all the hydrogen bonds in the water system has been broken. And then the main edge typically follows the intensity of the pre-edge, and then the post-edge is typically taken as a sensitive for the tetrahedral coordination. Increased level of tetrahedrality in the system means a higher post edge. You can see this temperature dependent changes to the spectrum here from a study where the lowest temperature line measured at 1.6 degrees centigrade is repeated here as a black line throughout the different temperatures. So now there's a lot of debate on the structure of water, and this method has been used just as X-ray absorption spectroscopy has been used to study the different effects of thermodynamic conditions on the local atomic network around molecular network around the water molecule. And for example, the question that how the hydrogen bond network looks like, what is the microscopic structure of water, is a big mystery, because water is a very complex system to simulate. It's also a very complex system to study. And one of these, if you're working with an XAS spectra, one of the things that comes to mind is how to interpret these changes to the spectra. So we have two black boxes actually there. We don't know if, for example, we could do a simulation of this spectra based on molecular dynamics simulations to get the structure and then calculate the spectra from the structure. But we don't know if the molecular dynamics simulations would deliver the correct structure of water, and then we don't know whether spectral calculations would give perfect agreement with the experiment. So there's a lot of research going on in interpreting the water, liquid water structure based on this. Sorry, excuse me, just take a sip of water. Are there any questions at this point?
Yeah, we have a question. Neil, would you like to pass on your question here?
Yes, can you all hear me?
Yes.
Oh, brilliant. So yeah, Simo, I was really interested in the ant example you showed. And I wondered if anybody had taken this X-ray Raman imaging approach to the analysis of highly radioactive materials through containment, because that could be quite exciting, particularly if you have like a you know, as a very radioactive fallout particle, for example?
There is actually quite a bit of actinide research going on. So we have been involved in measurements of uranium to plutonium systems. And there, of course, the imaging helps you to go to get rid of spurious signals from the sample environment. For imaging as such, I mean, then one is limited by the absorption coefficient of the sample, so one could not really go through lots of material. So that's why these carbon systems are good, because the photoabsorption cross section is pretty well, relatively low, so that one has an access to the 3D structure. Heavy elements will stop the beam, and then you would get the surface information.
Yeah. In this context, though, Neil, there's a second issue, and this is something Simo mentioned, which is that the X-ray Raman scattering does not have self-absorption problems, and so, for example, measuring the oxygen K-edge in uranium oxides by fluorescence mode or whatever your favorite method is with soft X-rays tends to give different results on every sample. So some years ago, Steve Conradson and collaborators and I did some measurements on various uranium oxides with X-ray Raman and compared it to SSRL results. And the Raman came out looking poorer in statistics, but hopefully better in accuracy.
Excellent. Okay, I'll check those papers out. Thanks so much.
Good. So I'm soon in the end, and I'm also soon out of time. So I just wanted to mention that then we wanted to do a systematic study of known structures that have this water molecular network, and we of course can access different ice phases. So condensed phases of water, there are numerous different crystalline and amorphous phases, and this shows a part of the phase diagram of water. If you compress liquid water in room temperature, you can go to ice phase called 6. So these are labeled with numbers in basically defining order. So there's an ice 6, and then which turns into ice 7. Ice 6 has a tetragonal structure. Ice 7 is cubic. And then if you lower the temperature from ice 7, you can go to ice 8, which is otherwise the same than ice 7, but it has a full proton order, while the others are proton disordered. So there's a lot of controversy, and at that time when we did this study, it's some time ago already, and a lot of new things have happened back after that, but nevertheless, some of the controversies was, for example, is the proton order one of the key things that that affect the spectra. So we wanted to take a look at these spectra of these ice phases, and that now you can do that with X-ray Raman spectroscopy with the diamond anvil cell. So it turns out that these are the ambient pressure phases. This is liquid water with 1 gram per cubic centimeter density. It has this pre-peak, main edge, and the post-edge structure. In contrast, ice 1 hexagonal has a much lower pre-peak than the liquid water, because basically it has less broken hydrogen bonds, ideally none. And then you have a strong peak here at the post edge because it has a fully tetrahedral coordination. So these are the fingerprints that were considered at that time. And then we go to these ice phases, ice 6. All of these, I should mention, have a fully bonded hydrogen network. Ice 6 has already a little, quite diminished post edge and slow starting increase of the pre-edge structure. And when you go to ice 7 and ice 8, they have very similar density and otherwise very similar structure, except for the proton disorder. They look like this. They have basically lost this post-edge feature, which is this hump is strong in the ice 1 edge. And now using this, trying to understand what these spectral features mean. In this case, this pre-edge that is increasing in the ice 7 and ice 8 cannot be due to distortions to the hydrogen bond network, because we know that there are none in these ice phases. Looking at this, what could be a consistent way of looking at this, that there's actually this spectral changes that decrease the pre-edge, increase the main edge, and decrease the post-edge are related to density, so that the lowest density ice phase has a strong post-edge, for example, and the highest density has the minimum. So then one can quantify the spectra in many different ways, and we did density functional theory calculations and many other things. But a very simple thing is to take the pre-edge to main edge intensity ratio after fitting the spectra with Gaussians, and then plot that as a function. Sorry, it was the main to post edge ratio, and then plot that as a function of density. And one can see that it follows kind of this line, except that liquid water is an outlier in this plot. Now, why this density increases in these systems is not because the local first hydrogen bonded neighbors would come closer. They actually stay intact in their positions, more or less. The first coordination shell in this phases doesn't change. It's the second shell that comes closer and eventually at highest densities even penetrates inside the first coordination shell. So you have non-hydrogen bonded molecules closer than the hydrogen bonded molecules around the central water molecule. So now we could say that basically the spectra correlate very well with the second shell distance, and we could basically then make a conclusion that the second shell distance is one of the key parameters. And I think that was a nice example of what one can do with the X-ray Raman spectroscopy. And going back to the yesterday's Jerry's presentation, the question was presented to Jerry that how you could make this measurements more complicated because they were coming too fast. This is one way to do that. Go to very tiny samples in high pressure and complicated sample environments, and that makes the efforts again much more complicated. I must be already over time, so I just wanted to thank a few of the key collaborators. There are many more that I couldn't list here, but otherwise, are there any questions from the audience at this point?
That was wonderful, Simo. Great examples. Thank you very much for putting this together. We've got two questions. Evan, do you have a mic? Can you ask your question? Evan Jarman?
Hi, can you hear me?
Yes.
Yes.
Yeah. So my question, this was back when you were discussing the liquid phase results. Given the high energy of the incident beam, is there substantial radiolysis of the liquid phase water? And if so, can you comment on spectral distortions or compatibility with the cell design?
Yes, very good question. So yes, this radiation damage is a problem for the water systems, and what turns out that if you have a still water, liquid water in ambient conditions, otherwise you would create a bubble immediately at the place where the beam hits. So for liquid water, one is forced to use a flow cell, so replenishing the sample all the time. And for high pressure, actually, it seems that the beam damage is not such an issue because the pressure is so high that maybe I'm not able to probably explain that better than that. When the pressure is high, then this you create basically OH radicals. You break a molecular bond, right? And these OH radicals then start breaking other bonds, and you create a bubble of gas phase system. But this doesn't happen in a high pressure cell. This is just an experimental observation. I don't have a really molecular level explanation to that at the moment.
All right, thank you.
All right, Tim Hyde, do you have a microphone available? You've got a question?
Hopefully so. Can you hear?
Yes.
Yes.
Yeah. Okay. Where else other than ID20 at ESRF can you actually do XRR measurements? And I guess a subsidiary to that is the EVS upgrade. Is that enhancing anything, or is it making it more complex to do those sort of measurements at ESRF?
Right, thanks. So there are definitely many other places. All major synchrotrons have a setup for doing X-ray Raman spectroscopy, and that was touched upon yesterday by Jerry. There is Jerry personally contributed to the development of the LYRIX spectrometer at the APS, which is going to go through an upgrade, right? Maybe Jerry can update on the upgrade of that part. And there's a spectrometer at Spring 8, there's a spectrometer at Soleil, there's a spectrometer at Petra 3, many other places. So SSRL, definitely. And right.
Okay.
And then the EBS upgrade of ESRF will not change so much for the spectroscopy. This is a general thing. Many other methods benefit from coherence, for example, but it does improve the beam quality, for example, in terms of the focus. So the old focusing optics can reach 10 by 20 micrometer spot size on the sample. 20 on the horizontal and 10 in the vertical, and this is expected to go to a round beam of 10 by 10. This is definitely one thing.
Okay, thank you.
Jerry, I had a question I had posted a little earlier. This is Faisal.
Oh, go ahead, Faisal. I'm sorry, I missed it. Go ahead.
Yes, this is actually for anyone who wants to chime in. But especially for Simo and Jerry. Is there an analog to using the spectral features in eels using Kramer's chronic transforms to get optical properties? Is there an analog to that in XRS, and is it being used?
Yes, it's being used, and actually it's maybe slightly bit more relevant for the valence excitation part. So when I showed the diamond spectrum at low momentum transfer, you have the plasma on line shape,
Yes.
and this is being used to analyze the spectra from that point of view. It's basically everything is equivalent to EOS in a way, except that the first bone approximation is better hold in elastic X-ray scattering. But otherwise, all these EELS and LNS methods are perfectly just as valid.
Okay, we've got one last question, though this actually suggests someone that we should invite to give a next X-ray Raman talk, and that's whether you can comment on the orbital image as a tool to solve condensed matter problems.
The orbital image. So, yeah, right. I mean, there are many actually ways to look at the orbital shape of the orbital and the radial extent of the radial part of the orbital by basically taking a single crystal sample and rotating it and measuring the X-ray Raman spectra. One can then reconstruct the molecular or the orbital shapes. This has been shown by the group of Hao Cheng recently, and then for that gives you the shape, the angular part, and then the momentum transfer dependence can give an access to the radial part, because basically what one is looking at, the S of Q omega is a Fourier transform over excuse me, space and time of the electron correlation function, and then basically the transition matrix operator shown yesterday by Jerry can be traced back to look at the strength of these different multiple excitations can give an access to the Fourier transform of the radial part as well. So it's actually an interesting new emerging field to look at that. I don't know if that was the answer to your question, or did I answer the right question?
I expect you did. All right, not to keep everyone from either going to bed or waking up, depending on where you are. I wanted to say that we doubled attendance today, so our doubling period is 1 day, and we're well ahead of COVID that way, which in this context I think is a good thing. And
the mortality rate is lower.
Even better. Yeah, well, as far as we know. So could you scroll back to the very first page, Simo, with the that link on it?
Right. I can do it by doing this.
Yes. Yeah, so in the chat, I reminded everyone of my email address. And also, I think that shared folder link will work. The tinyurl.com global Zaps talks. And either contacting me or looking there will let you schedule yourself or a friend to give a talk. Right now, the next scheduled talk is on Monday. If someone wants to give one tomorrow, I can quickly make the link and send out the mailing list on that. If you have friends who you want added on to the mailing list for when there's talks, just send me an email and I'll do that. And I'll also send an email out, like I said before, once I figure out YouTube, so that it's easier to stream the recorded lectures. But all of them are being recorded. And Simo, if you could send me a PDF of your slides, that would be terrific.
Yep, no problem.
Okay. So we're at 9:40, which is kind of our target end time. And again, thank you everyone for participating today, and stay healthy.